The following audiobook contains AI-generated content and may contain errors. MyAudiobooks.ai presents Antarctic Air Routes: Why Airlines Avoid the South Pole. Antarctica is not sealed off by a universal aviation ban. Aircraft can fly there, and some do. The stranger fact is that ordinary scheduled airlines still treat the Antarctic interior almost like a hard stop. A globe makes the question feel simple. If the shortest path between two faraway cities seems to cut across the bottom of the world, why not send a jet that way? But airline route planning is not drawn on a globe in perfect weather. It is approved by dispatchers who must justify, before departure, that the aircraft can handle engine trouble, medical emergencies, fuel limits, communications gaps, and a sudden need to land somewhere safe. That is the real mismatch. The map suggests open space. Airline operations see a huge region where the normal safety net thins out. The central idea is simple, but it changes the whole story. The problem is not a continent-wide prohibition. The problem is whether a real flight, on a real day, can always reach a usable alternate airport after something goes wrong. In long-range airline operations, this is the logic behind ETOPS, short for Extended Operations. It is an approval framework that governs many twin-engine flights far from airports. The international version is often described as EDTO, Extended Diversion-Time Operations. International Civil Aviation Organization guidance and European practice use that broader language because the core question is diversion time, not just the number of engines. The Federal Aviation Administration's Extended Operations guidance follows the same basic principle. It focuses on how far an aircraft may be from an adequate airport, measured in time, under approved assumptions. It is not a blanket rule saying airplanes may never cross Antarctic airspace. A diversion is the decision to leave the planned route and land somewhere else, because continuing no longer makes sense. The trigger might be an engine problem, smoke, a medical emergency, a pressurization issue, or anything else serious enough to demand a landing. An adequate airport is a place that can physically and operationally accept the aircraft. It needs enough runway, the right surface strength, usable navigation or approach procedures, and emergency services appropriate to the aircraft. A suitable alternate goes further. It is adequate, and it is expected to be usable for this exact flight at this exact time, with the forecast weather, runway condition, staffing, rescue and firefighting coverage, and aeronautical notices all considered. That distinction matters in Antarctica. A runway can exist on a map, on ice, or next to a research station, and still fail as a dispatch alternate for a commercial airliner. If the weather is below limits, if rescue services are not available, or if a large jet cannot be handled, the airport may be real without being useful for airline dispatch. The same is true if passenger shelter is inadequate, or if the aircraft cannot be repaired or recovered. Several other terms help frame the rest of the problem. The geographic South Pole is where Earth's rotation axis meets the surface. The magnetic pole is different. It is tied to Earth's magnetic field. It moves over time, and it affects compass behavior. A fuel's freezing point is the temperature at which the fuel can begin to form crystals that threaten reliable flow. An operating margin is the buffer an airline wants above a limit, because flying safely means staying away from the edge. A great circle route is the shortest path across a sphere, even if it looks curved on a flat map. Put those ideas together, and the Antarctic problem starts to look less mysterious. Airlines do not simply ask whether a jet can survive over ice. They ask whether the entire route remains inside a supported recovery system. ETOPS and EDTO make reachable alternates the backbone of long-distance route planning. A dispatcher cannot treat a flight path as a thin line across empty space. The route has to sit inside a corridor where, from every point along the way, the aircraft can reach an approved alternate within the allowed diversion time. That approved time depends on the aircraft, the operator, the equipment, the regulatory approval, and the scenario being planned. The exact number is less important than the operational shape it creates. If a route crosses a region where alternates are too far away, the corridor breaks. The flight may be technically possible, but it becomes hard to release as routine scheduled service. Antarctica is a poor place to build that corridor. The continent has airfields, but they exist mainly to support science, national Antarctic programs, and specialized logistics. McMurdo Station is a major United States hub, and it has used prepared ice and snow airfields, including Pegasus Field in the past and Phoenix Airfield more recently, for wheeled aircraft. Those operations are built around seasonal conditions, trained crews, specialized ground support, and mission planning that begins with the realities of the ice. That is very different from a commercial alternate for a wide body full of passengers. A diverted airliner is not merely looking for a flat place to touch down. It brings hundreds of people, crew duty limits, baggage, medical needs, food, heat, toilets, security concerns, maintenance requirements, and a need to continue or recover the journey. If the aircraft lands safely but cannot be refueled, de-iced, inspected, repaired, or flown out again, the landing solves the first emergency and creates another. Rescue and firefighting assumptions also matter. Large passenger aircraft require trained personnel, vehicles, access, and response capability. Remote Antarctic stations have highly capable teams for their missions, but they are not built as ordinary recovery airports for unscheduled passenger jets from multiple airlines. Weather widens the gap. Antarctic wind, blowing snow, low visibility, runway surface changes, and seasonal darkness can erase an alternate from the plan even when it exists physically. A dispatch release cannot be built on hope that a remote ice runway will still be usable hours later. So one major reason scheduled airlines avoid the Antarctic interior is infrastructure. The continent has aviation, but it does not have a dense, redundant network of suitable alternates. Without that network, the normal safety logic of long-haul airline flying starts to fail. Cold in Antarctica is not just uncomfortable. It is an operational limit that affects fuel, engines, instruments, hydraulics, batteries, seals, and the people who have to work around the aircraft. Fuel is the clearest example. Jet fuel remains usable only while it stays above its approved low-temperature limits, with enough margin for safety. The freezing point is a certified property of the fuel, but airlines do not plan to scrape along that boundary. They track the buffer between actual fuel temperature and the limit, because that buffer can shrink during the flight. Fuel in the wings can become cold-soaked. That means it cools gradually as the aircraft spends hours at altitude in very cold air. The outside air may be far colder than the fuel's limit, and the fuel temperature changes slowly through the tanks. On an ordinary route, dispatchers and crews can manage that with fuel choice, altitude and speed decisions, and monitoring. Over Antarctica, the issue becomes more demanding because a diversion may mean even more time in severe cold, followed by a landing at a remote site where the aircraft may sit exposed. As fuel approaches its low-temperature boundary, crystals can form and threaten the filters and lines that feed the engines. Water contamination can also freeze into ice in the wrong places. Filters protect engines, but restricted filters can reduce fuel flow. The aircraft has sensors and procedures to detect fuel temperature trends, but the safest plan is to preserve margin before the warning signs become urgent. The cold also complicates engine starts and ground handling. Engines, auxiliary power units, lubricants, pumps, and batteries all behave differently in extreme low temperatures. An aircraft that lands unexpectedly in Antarctica may need heated equipment, trained mechanics, spare parts, ground power, and time. If a system cools beyond what the recovery team can manage, the aircraft can become stranded even after a successful landing. Performance planning changes too. Cold, dense air can help some aspects of takeoff performance, but Antarctic operations are shaped by runway surface, wind, visibility, braking action, contamination, and support equipment. An ice runway is not the same operational environment as a paved international airport, even if both are long enough in theory. That is why polar fuel planning tracks temperature across the whole mission, not just at takeoff. Fuel can cool after loading, during cruise, during the diversion, and on the ground. Every stage can remove a little more buffer.
A route that looks acceptable by distance may become unattractive once dispatchers ask how much cold weather margin remains after an abnormal event. Navigation near the poles adds another layer. The geographic South Pole and the magnetic pole are different ideas, and neither behaves like the simple compass rose many people imagine. At the geographic South Pole, longitude lines converge. Directions become conceptually strange because every direction away from the pole points north. Near magnetic pole regions, magnetic compasses become less reliable because Earth's magnetic field can be steep, weak in the horizontal direction, or rapidly changing across short distances. A heading based on magnetic north may swing or lose practical value. Modern airliners do not navigate Antarctica with a single magnetic compass. They use true headings, inertial reference systems, GPS, flight management computers, and carefully planned procedures. International polar guidance and national rules call for long-range navigation redundancy, so a crew does not depend on one source of position information. The aircraft needs independent ways to know where it is and where it is going. Communications have their own complications. Ground-based navigation aids and radio stations are sparse across Antarctica. Very high-frequency radio depends heavily on line of sight, so it works best when aircraft and ground stations are within range of each other. High-frequency radio can reach farther, but it depends on the ionosphere, and the ionosphere can be disturbed by solar activity. Satellite communications can help, but coverage and reliability depend on the satellite system, the aircraft equipment, and the geometry of high latitudes. That is why polar operations include space weather awareness, communications plans, and backup procedures. None of this makes Antarctic flight impossible. It makes routine dispatch more complex, especially when the same route already struggles with alternates in cold weather recovery. Then comes the route itself. A great circle route is the shortest path across a sphere. On a flat map, it can look like a strange arc, even though it is efficient on a globe. Many long-haul flights use that geometry every day, especially across the northern high latitudes. But Antarctica does not sit under the densest web of global city pairs. Many useful polar shortcuts run over the Arctic, linking North America, Europe, and Asia through Alaska, northern Canada, Greenland, Scandinavia, or Russia when airspace access and conditions allow. In the southern hemisphere, routes between Australia, New Zealand, South America, and southern Africa can arc far south over the Southern Ocean. Even so, crossing the Antarctic interior often adds more operational burden than it removes in flight time. Airlines do not optimize only for the shortest line. They value schedule reliability, fuel predictability, maintenance support, crew planning, passenger recovery, and the ability to recover from bad weather or a mechanical fault without a crisis. A small theoretical time gain rarely justifies a route that makes every abnormal situation harder. That is the economic side of the same safety problem. A route can be legal under some assumptions and still be a poor product for daily airline service. The strongest proof that Antarctica is not forbidden airspace is that people really do fly there. Antarctic sightseeing charters have taken passengers over the ice from countries such as Australia, usually without landing. Scientific and government logistics flights support research stations. United States and Australian Antarctic programs move people, cargo, fuel, and equipment through carefully planned seasonal operations. McMurdo is the best-known hub for large-scale Antarctic aviation. The Amundsen Scott South Pole Station is served by aircraft built or equipped for the environment, including LC-130 ski-equipped aircraft. These aircraft can land on snow and ice surfaces that ordinary airliners are not designed to use. Other specialized aircraft support stations and field camps according to weather windows, runway conditions, mission needs, and available support. Those flights matter because they show what the real answer is. Antarctic aviation works when the aircraft, runway, season, weather forecast, crew training, fuel plan, communications, maintenance support, and recovery plan are all designed around Antarctica from the beginning. They do not prove that routine scheduled overflights are easy.
A sightseeing charter can choose a narrow route, a season, a weather window, and a return plan. A logistics mission can carry specialized equipment, operate with Antarctic-trained crews, and accept mission-specific delays. A scheduled airline carrying ordinary passengers on a global timetable has a different burden. It needs repeatability. The Arctic comparison makes the lesson clearer. Airlines have operated polar-certified routes over Alaska, northern Canada, Scandinavia, and Russia because the northern high latitudes have more infrastructure around the rim. There are more airports, more settlements, more military and civilian support points, and more practical options for diverting and recovering passengers. Arctic flying still demands cold weather planning, communications procedures, navigation redundancy,
regulatory approval, and careful dispatch. But the pieces line up more often. Antarctica stacks the same manageable problems in the same place. The alternates are too few. The weather is harsh. The cold reduces margins. Communications and navigation require extra layers. The recovery plan is difficult. The market benefit is usually modest. Each issue can be handled in isolation. Together, they make the Antarctic interior technically possible for specialized missions and commercially unattractive for routine airline service. If routine Antarctic overflights were to become normal, several things would need to change. Airlines would need more reliable, suitable alternates, with runway capability, rescue and firefighting coverage, passenger shelter, fuel, maintenance, and recovery capacity. Aircraft and fuel planning would need stronger cold weather margins, not only for flight, but for an unexpected stay on the ground. Communications and navigation would need resilient coverage, redundant systems, and proven procedures for high-latitude disruption. Regulators would need to approve operations based on demonstrated support, not just on a clean-looking line across a map. So the final reframing is this. Airlines do not avoid Antarctica because the map says they must. They avoid it because today's dispatch rules, infrastructure, weather, fuel margins, communications, recovery planning, and economics usually say they should. The next time a polar shortcut looks obvious on a globe, ask the airline question. If something breaks halfway through, where does everyone safely go? That single question turns Antarctica from empty space into a demanding operational system. This concludes